All right, this morning we're going to start talking about reactions of aldehydes and ketones, um, which of course will involve us going over the nomenclature of those two functionalities, some structural components as it relates to reactivity, and then of course we begin with the preparation of those two functionalities that then allow us to talk about the reactions, the standard format we do when we talk about new functionalities. But we're going to spend a few minutes before we start doing that talking about carbonyl compounds in general, because the rest of the semester we're basically going to be dealing with the carbonyl functionalities. We're starting with aldehydes and ketones because of their similar reactivity, but then we're going to go through all of the different functionalities that fall under the category of carboxylic acid derivatives, like acids themselves, but then esters, acid chlorides, amides, acid anhydrides, all those other functionalities. And we're going to take them, one at a time. But before we begin talking about all those different carbonyl functionalities, I want to do just basically what I call an overview of carbonyls. So that'll give us kind of a starting point. So as we're going through these, we know what the actual comparison is between those different groups. And so in the overview of carbonyls, what do we know about our carbonyl functionalities? We said they all have in common that carbonyl group, which was a C that's doubly bound to an O. Okay, and always bounded to some R group. Okay, and then the other side of the carbonyl was attached to something. And whatever is in this box basically defines what kind of carbonyl functionality it is. And so what we call this is the acyl fragment. And so it is basically what is common to all of our carbonyl functionalities. Okay? And so then all that's changing is what's in the box. And so, for example, if I put an H in that box, it's an aldehyde. If I put an R in this box, it's a ketone. If I put a Cl, or you could also do Br, but it's typically Cl, you have an acid chloride. You put Or in the box, you have an ester. And you see how this is going? You put an OH in here, it's a carboxylic acid. You put an NHR, nitrogen containing substituent, it's an amide. Okay? And we could go on, if you put an O, then a carbonyl, you have an acid anhydride. But basically the point here is what's defining the functionality is you have the acyl group in common for all carbonyls, and it's just that one group that's in the box that defines the exact type of carbonyl. And then as we're going to see, that basically then defines the two different types of reactivity that the carbonyl functionality will undergo, because it's either going to undergo one major set of reactions or another major set of reactions, depending on its identity. All right? And so looking at reactivity, kind of said in general just a second ago, but more specifically, let's look at this. Depending on what is attached to the acyl group, we basically have two types of reactivity for our carbonyl compounds. And it all depends on what's in the box. The first of those is aldehydes and ketones. Now, as we're beginning to do this, I want you to remember, we've been introduced to this several times already. What is the difference between a nucleophile reacting with a ketone and an aldehyde versus a nucleophile reacting with an ester or an acid chloride? We've seen that when we talked about Grignards. We've seen it when we talked about reductions. Now we're seeing it again, but in a very general sense. if you understand these two things, you'll understand the reactions for the rest of the semester. It's really that easy. So aldehydes and ketones have a certain reactivity because that acyl group that we just looked at is bound to, remember, an H or a carbon, okay? And so basically an H or an alkyl group, okay? So that basically means your H or R will not support a minus charge. Therefore, it is not a good leaving group. Okay? And if it's not a good leaving group, you don't see any reaction mechanistically that would require the R or the H acting as a leaving group. So going back to the acyl group, what that's basically saying is whether this is an R or an H, neither one of these groups would support a minus charge, so you're not going to see it leaving as a leaving group. And as we're going to see in a minute, that's what then leads to addition reactions instead of substitution. Substitution reactions require a leaving group. Okay, addition reactions occur otherwise. Okay, so that's what kind of defines the reactivity. Now, the other category besides aldehydes and ketones are simply what we call carboxylic acid derivatives. These are the carbonyl functionalities that are basically derived from carboxylic acids. So that is carboxylic acids themselves, esters, acid chlorides, amides, esters, see if I'm leaving any, anhydrides, let's call it acid anhydrides. All of these are carbonyl functionalities we've learned, and all of these fall in the category of carboxylic acid derivatives. So their reactivity, they're going to react in this second type of category, not the additions that aldehydes and ketones undergo. Because here, in every one of these functionalities, we have our acyl group and is attached to some X, where this X will support a negative charge. And if it supports a negative charge, it's a good leaving group. And therefore, the reactivity of these functionalities tend to be substitution because this X can in fact be a leaving group, allowing substitution of a nucleophile instead of addition. Okay? So that's what's judging, or I should say determining our reactivity. Okay? Because basically, for either type of carbonyl, we're going to have a carbonyl carbon. I'm purposely not putting anything on these ends. So we're just focusing on the carbonyl. That carbonyl has the reactivity that this carbon is electrophilic. And therefore, nucleophiles are going to react with it, or bases, one or the other, okay, because it's behaving as an electrophile, okay? And so basically then, there are 4 different types of reactions that these carbonyls can undergo. And you're going to see that we're basically mainly going to talk just about 2 of the types. We usually are able to talk about the other 2 just briefly at the end of the semester, but it's mainly just 2. And the different types are determined by the mechanism. So you can almost say that there are only 2 mechanisms left to learn for the rest of the semester. 4, but the last 2, the third and the fourth type of reaction mechanistically are really the same as the first 2. All right, which will make sense when we get there. So there's really not a lot to learn mechanistically from here on out. And basically these types are nucleophilic addition. And so that means that a nucleophile is going to add to my carbonyl. And so what we've already talked about, that lets you know that if it's going to be a nucleophile adding that gives us our product, that's going to happen on aldehydes and ketones because they do addition, because they have no leaving group. Okay, the second type is nucleophilic substitution. And that's going to be where a nucleophile substitutes into the carbonyl functionality. And that then would require a leaving group. Therefore, nucleophilic substitution is what all the carboxylic acid derivatives undergo. Okay? Third type of reaction is alpha substitution. And that is a reaction that's not occurring directly on the carbonyl, but it's occurring in the alpha position. So remember, when we get to that, what we're going to see is, instead of reacting at the carbonyl, an alpha substitution is a reaction that's occurring once removed from the carbonyl, which we call the alpha position. And then the fourth type is carbonyl condensation. And that's going to be where one carbonyl compound reacts with another nucleophile electrophile. Okay, so that's 2 different carbonyl compounds reacting together. Okay, and so we'll touch on all 4 of these, but by far these 2 are the most important types of reactions we have left to discuss. All right, so let's kind of do just a very general introduction to the first 2 types of reactions before we get specifically into the different functionalities. So let's just look at nucleophilic addition. And we're going to look at it from a mechanistic standpoint. Okay, so in general, and I'm going to do it this way, A and B. So you have your carbonyl with 2 things attached to it. And I'm going to change my mind. Let's do this as an R. Okay? No, I'm going to leave it as an A. So I'll take a break there while you catch up to my changing my mind over and over again. A and a B. I'm emphasizing the fact that my carbonyl has 2 things attached to it. All right? And if you're doing an electrophilic addition, the first thing that's going to happen, and I'll just use my standard, abbreviation of NU for the nucleophile with a minus charge. How is this going to initially happen? We have a nucleophile. It's going to react with the electrophilic site in the molecule. So the nucleophile is going to come in and react right there at the electrophilic site, which is the carbonyl compound. And that's always going to break this pi bond and move the electrons out to the oxygen. Mechanistically, we've seen this before. It's what happened with Grignards, and it's what happened with the reductions. Okay? But we're just emphasizing this again. That does what then? Your electrons are pushed out to the oxygen. You have your A that's already present. And let's do this with stereochemistry. So you have your A and your B that were initially attached, and so the new bond you're forming is to this nucleophile. So basically what you're doing is taking an sp2 hybridized carbon here, that's the carbonyl, and it's becoming sp3 hybridized, okay, because you're adding something to it, pushing electrons away from that center, okay? And what you form here is a tetrahedral intermediate. Okay, we're going to see this tetrahedral intermediate in both of the first two mechanisms. Okay, because initially we always have the nucleophile add to the carbonyl. Okay, now once this intermediate forms, what's going to happen? What we've seen already is what happens if you have an acid present in your workup. Remember, we said we simply protonated that intermediate and we ended up with the alcohol product. That's going to be one of the fates, but it's not the only one. Okay? And so I'm going to show you now what the two possible fates are when you have nucleophilic addition. Okay? And they're very similar. So let's start with a carbonyl with two R groups. So we're looking at a ketone. It'd be the same if it were an aldehyde. There are two different conditions of nucleophile we can add. One is a negatively charged nucleophile, which is like we've seen already with the Grignard and the reduction. But you can also envision a situation where you're adding a neutral nucleophile. So I'm going to write that down. Negative and neutral. And let me make sure that you can see that that's an N for the nucleophile. Okay, so you have your ketone or aldehyde. You have two different conditions, either negatively charged nucleophile or neutral nucleophile. In both cases, you're going to have that nucleophile reacting with the electrophilic carbon of the carbonyl, which will displace the pi bond and move the electrons out to the O. So they initially react the same way. And so you're going to form in each case a tetrahedral intermediate where I have my R prime, and then my nucleophile that's added. And then over here, I'd have a very similar intermediate. It's going to be tetrahedral because I push the electrons out to the O, put in my R groups, and then I have my nucleophile. But here, my nucleophile added neutral, so it has a plus charge on it. It's the only difference between these two situations. Negative nucleophile adding, it adds then as the nucleophile. If it was neutral when it added, now it has a plus charge. And we understand mechanistically why that occurs. Then each one of these things then does something a little different. Okay? In this particular intermediate, we saw that you just work this up with an acid. And when you work it up with an acid, you will get the alcohol as a product. And I'll show that in a minute. But over here, something different happens. It expels water. And it gives a slightly different result. So by the magic of digital technology, I'm just going to erase this all right now because you're able to pause and make sure that you've got everything down. And so if I were on a big board, I would have just gone below that, but I'm not on a big board. So remember here we were saying that you're coming down with H plus from here, and here we said expels water from that other intermediate. So what you form here is basically you protonate that oxygen. So you're going to end up with what we've seen before, the alcohol product, right? And in the cases we've already seen, if this nucleophile is a Grignard, then you have a tertiary alcohol. If this was a hydride, an H minus, then you have a secondary alcohol, right? But it's a straightforward addition product. But over here, if you expel water from that intermediate, what you actually form, you reform a double bond, but it's a double bond to the nucleophile. And so you've lost the carbonyl oxygen as water, you've lost a proton from the nucleophile, And the OH minus that would be protonated, that makes O, two H's, water. We're going to see this more detailed mechanistically when we do the exact specific cases, but these are the two results that you can get depending on whether it's a negatively charged nucleophile or a neutral nucleophile. And we're going to see examples of both of these types of reactions. Okay, now the good news is the example of this reaction is when you take an amine and you react it with a ketone or aldehyde, this is the product that you get. And we're going to see that that's because amines can add as neutral amines. They're nucleophilic enough. And so mechanistically, we're going to look at that, maybe not in today's lecture, probably the next lecture. Okay, but that's really the only example that we look at. Okay, there may be one other, but it's not the typical result. This reaction, the simple addition, is what we see. The examples we've already looked at are Grignards and hydrides, which are both reactions we looked at in the alcohol chapter. So those are examples of reactions that go through this type. Okay, but again, by far, most of the reactions we look at fall under this category. All right. So the other type of reaction in general, remember, was the nucleophilic substitution. Nucleophilic substitution. And a nucleophilic substitution reaction occurs a little different. Let's start with showing our carbonyl like this because we're emphasizing the fact that there's some Y attached here. And this Y, in order for a substitution to occur, this Y has to be a good leaving group. And therefore, when we're talking about this general type of reaction, it's the reaction that occurs on carboxylic acid derivatives because they have a leaving group attached to the carbonyl. All right, and so first thing that's going to happen is you have your nucleophile. Okay, just like we saw in the other type, nucleophile reacts with the electrophilic carbon of the carbonyl, breaks the pi bond, moves the electrons up to the oxygen, giving that same tetrahedral intermediate. Isn't it nice that both of these reactions mechanistically start out exactly the same? It's going to make it easy to remember. Okay, so there's my Y, and then here's my nucleophile that is added. So initially, we've simply added, right? But now at this point, instead of adding an acid to protonate this, or having water expelled, here we have this leaving group. So these electrons can come back in to reform the carbonyl, and when they do, you lose your leaving group Y, okay, which results in the formation of this product, which is simply the substitution. Now I'm going to show you how simple this, just like the other one, all you're doing is adding the nucleophile and making the carbonyl into an alcohol. Here you have this Y that's in the box, and it's a leaving group. And you're reacting it with some nucleophile that's going to substitute. So predicting the transformation here is what's in the box Y is just substituted with nucleophile. That's all there is to that transformation. So it's really easy you just look at what the nucleophile is and substitute it for Y. That's how all of these nucleophilic substitution reactions occur with carboxylic acid derivatives. All right, so if you want to look at a simple, quick example of that, we'll use a generic carboxylic acid derivative, and this reacted with methoxide. Okay, knowing what I just told you, what is the result of this going to be? If this is the nucleophile, it's going to substitute in for what the Y is. So I just put that in that place, and oh, look, I formed an ester. Okay, and so the interesting thing we're going to see as foreshadowing is you're going to have some carboxylic acid derivative here, depending on what the Y is, reacting it with a nucleophile, and you're forming what? Another carboxylic acid derivative. So this is just transformation back and forth between the same type of functionalities. All right, so that's how a nucleophilic substitution would look. And I'm not going to, in general, go over alpha substitution or the carbonyl condensation, because I'm going to leave those mechanisms until later, because we're not going to use them in a while, and there's no reason for you to have that model yet. Okay, and so let's start with aldehydes and ketones now. So let's do nomenclature of aldehydes. So now we're starting specific functionalities. We'll do aldehydes and ketones kind of together because their reactivity is basically very similar. Okay, but their nomenclature is a little different, so we have to separate for that. So nomenclature of aldehydes. Here are the rules. Now remember, as we go through nomenclature over the first semester, the detail got a little less because foundationally we know how to name alkanes, we know how to name a lot of functionalities now, so we don't have to go all the way back to square one when we're naming something, because basically in the rule you know how to name alkanes. So you basically name an aldehyde that's named by replacing the single E ending of the corresponding alkane with a new ending. And the new ending for an aldehyde is going to be Al. So you're dropping the E of the corresponding alkane and adding Al. Okay? The longest continuous chain must contain the aldehydic carbon, so the carbon of the aldehyde. Okay? And then this to me is a no-brainer because you know all of this just from your experience. But the aldehydic carbon is always numbered 1. The reason is aldehydes are terminal functionalities. By definition, they're at the end of a chain because they terminate. You've got an H on one side, you can't attach anything to the H. So because it's a terminal functionality, it can always be numbered as 1 because it's always at the end. So you always start numbering at the end where the aldehyde is. All right? And that makes perfect sense. So let's look at examples. Start out relatively straightforward first. So we have this aldehyde. Okay, longest continuous chain containing the aldehydic carbon, straight across, always number it as 1. Okay, if this were an alkane, this would be butane. Okay, so to name it as the aldehyde, I drop the E and I add Al. Butanal. Okay, you notice how nal, not butanol. You have to make sure that you're enunciating so you don't get it confused with the alcohol. So butanal. Okay, what about this one? I'm going to erase this. So what about this one? Longest continuous chain must contain the aldehydic carbon. So that means I have to go up this way, and then I either go this way or this way. Oh, it's the same. So start numbering 1, 2, 3, 4, 5, 6, but it wouldn't matter if you had numbered out this way because you have 3 carbons on either side of this one, so it doesn't matter, it's symmetric. Okay, but that means that this is my substituent right here, right? Okay, so how would I name this? It's 3-propyl. Okay, then the alkane would be hexane. I'm going to drop the E and add Al. 3-propyl hexanal. All right, so very straightforward. Aldehydes are easy to name because they're a terminal functionality. Okay, but when your aldehydic carbon is a substituent, we always run into that situation, right? There's always something at the end of our rules that say, well, what if it's a substituent? So if it's a substituent, and this is going to be only on a ring, okay? Because otherwise, you're typically you may come up with a case where that's not true, but typically, if the aldehydic carbon is not in a ring, you're going to name it as the aldehyde, okay? And so an example of that is what if you have this not benzyl, this cyclohexane with an aldehyde attached. Now notice I'm making sure that you understand that CHO, is an abbreviation for aldehyde. So what if I had this aldehyde? To name this, you change the suffix. And you change the suffix to carbaldehyde. Carbaldehyde. I kind of ran out of room there. So carbaldehyde becomes the suffix, even though you're naming it because it is a substituent on the ring. And this carbaldehyde is basically added to the end of the name for the ring. So cyclohexane, right, is the name of the ring, and then you just add carbaldehyde to the end of it. Okay, so that's kind of a simple case. All right, everything you need to know about naming aldehydes is right there. Okay, so that brings us to nomenclature of ketones. So what's going to be the main difference between the nomenclature for aldehydes and ketones? There are really going to be two things. The first thing is straightforward, and that is my suffix is going to be different because I have to differentiate it from an aldehyde. So it's not going to be Al. It's going to have a different suffix. But what else is the difference between these two functionalities? Aldehyde was a terminal functionality. Ketone, no. In a ketone, that carbonyl can be located anywhere within an alkyl chain, not just at the end, like an aldehyde. Okay? And so your rules are going to be a little different because of that. Okay, first rule, name by replacing the E ending of the corresponding alkane with the suffix -one, O-N-E. So let me write that. Named by replacing the E ending of the corresponding alkane with a new suffix ONE. okay, which comes from ketone, right? Own, okay? So what do you think is going to be the next thing? The parent chain, remember, which is the longest continuous, the parent chain must contain the carbonyl carbon, all right? And then you're going to number from the end. Okay, you're on IUPAC. What do you think? Number at the end what? Nearer the carbonyl carbon. Those are all things that we would have come up with if we were making the rules ourselves. Okay, so by the magic of digital technology, and I'm getting marks all over my wall. My wife's gonna kill me. All right, so let's look at some examples. Start simple first. Something as simple as this. Well, the parent chain, longest continuous chain containing the carbonyl carbon. Start numbering at the end nearer the carbonyl carbon. Okay, and so with the aldehyde, it was always numbered 1, so the 1 was understood. We didn't have to put a 1 to identify the location of the carbonyl, but here we do, right? Not in this particular example, by the way, but normally you do. So we always do it, and that is your carbonyl is at the 2 position. And then it would be butane, right? If it were the corresponding alkane. So I drop my E and I add O and E, so it's 2-butanone. All right, what about this one? Oh, I threw you a little curve here because there's an alkene in here. Well, carbonyl, I'm naming it as a ketone. So therefore, I'm going to look at my longest continuous chain that contains the carbonyl carbon. And since I'm naming it as a ketone, I'm following the rule of numbering it such that the carbonyl carbon has the lowest number, because I'm going to number from the end nearest that carbonyl carbon. And so that means I'm going to, 1, 2, 3, 4, 5, number those out. And so what would the name be here? Well, I've got something at the 4 position, right? And that thing at the 4 position is the double bond. So pentene, right? Because I have to indicate that I have a double bond in the 4 position. That's just alkene nomenclature that we already know. But then I've dropped the E of the pentene. I've inserted the number position for where the carbonyl is, and I add my O-N-E. That's to make sure that we know the 2 goes with the own and the 4 goes with the ene. So 4-pentene to own. Okay? What about this one? So now I'm actually putting a carbonyl within the ring itself. And, don't let your brain explode here, because you basically would name it like you would expect. Okay? And that is, your carbonyl is contained within the ring. You always start numbering at the carbonyl carbon, right? So I'm going to start numbering there. That would be your assumption, and that is correct. And so then I would just need to number getting the lowest sum. That was our rules for cycloalkane. So, nothing changes. But here I can number 1, 2, 3, or I can number 1, 2, 3. So I could number in either direction. So how would I decide which way to go? Well, I'm going to call this isopropyl. And therefore, isopropyl comes before methyl. So I'd number it in this direction. Okay, and so therefore this is 3-isopropyl, 5-methyl cyclohexanone. Oh, I didn't have to put a 1 here. Why? Because we know the carbonyl in a ring has to be numbered 1. But if you wanted to put a 1 in there, you could. Okay? What about if your carbonyl is not actually part of the ring? What if you have to name it as a substituent? I'm watching my time here. Okay, we're good. So what we're looking at is what happens if you have your ketone as a substituent. Okay, and this is where, I wish I was in the classroom with you so I could do my put your pencils down and look at me. But put your pencils down and look at me. When we talk about this part of ketone nomenclature, we have to introduce that these substituent names are derived from the carboxylic acid names. And the problem is we haven't talked about carboxylic acid nomenclature yet. So this is one of these things in organic chemistry where it's the chicken and the egg thing. If we talked about carboxylic acid nomenclature first, so you would know it to do ketones, and there'd be things about carboxylic acids you wouldn't know in order to name them. So all of this nomenclature will become completely clear when we've done the nomenclature for all of the functionalities. But I'm going to show you just some easy examples of how we derive this substituent name, because we'll use some acids that you probably already know the name of. Okay? And so basically what we're doing is if you're naming this as a substituent, we all recognize that's basically an acyl fragment, right? It's the alkyl group to a carbonyl. So that is a ketone substituent. It's just the acyl fragment. So that's what we're actually naming. Okay? And it's named by taking the acid name, and I'll put corresponding carboxylic acid name. And so what that basically means is if there were an OH here, okay, that's the corresponding carboxylic acid. Okay? So you take that name and you drop the ic part of the ending and you add YL. And that creates the acyl fragment name, which is the carboxylic acid substituent name. Okay? So if we take a deep breath, we can go through this. Let's say that this is the substituent. You can see that that's a ketone substituent. Okay? So how would I come up with its name? What you do is you imagine what the name would be if you had the OH there. That would be the corresponding acid. And we all know that as acetic acid. Even though we haven't talked about carboxylic acid derivatives, all of us know acetic acid. That's a carboxylic acid. And that's the name of it. Okay? And so what we're going to do is drop the ic from that. And by the way, the acid name, it goes without saying because that disappears. But we drop the ic. So we're leaving the ACET, and then we're going to add YL. So that's, once you get the substituent name, it's acetyl or acetyl, depending on whether you're a biologist or a chemist. All right? Do you see how that was derived? What about this? As a substituent. Well, if it were the corresponding carboxylic acid, it would be this one, which would be benzoic acid, right? I'm going to drop the ic from the benzoic, and I'm going to add YL. Okay? See how I did that? The O remains. It's just the ic that I dropped. Okay? And so this would be what is left. Now, this is pronounced in a way, and the good thing, you can keep replaying this over and over again. You pronounce this benzoyl. Benzoyl. That's how you say it, benzoyl. And so this substituent is called benzoyl. All right? Now, when we get completed with all the functional group nomenclatures for the carbonyls, you'll be able to do these. So please be aware on that final test, which this material will be on, that test on the last day of class, we'll have already gone over carboxylic acid nomenclature also. So all of this, you'll have the whole picture. All right, so don't worry too much about that yet. All right. So everything we need to know about naming aldehydes and ketones we have just covered. Okay, and so that brings us now to where we really want to talk about preparation of aldehydes and ketones, because we're going to put off talking about the reactivity until we get to reactions. But right now we want to say, in terms of synthesis, if you learn this arsenal of reactions for aldehydes and ketones, how can we prepare those first to be able to do the transformations? So we're going to start with aldehydes. Now the beauty, if those of you that took Organic 1 before you took this course, you're going to see that there's a lot of review. Okay, we're going to start seeing that a lot this semester, where a lot of the reactions that I present to you, you'll go, oh, we already know that one. Well, there's some examples here. Preparation of aldehydes, just for a review, we already know some ways of doing that. First is oxidation of primary alcohols. Remember, just a few lectures ago, we talked about the fact that you could oxidize alcohols as one of the reactions of alcohols, and you could oxidize them, either to the aldehyde or to the carboxylic acid, depending on which oxidizer you used. All right, so we know that we can make an aldehyde this way. Second is oxidative cleavage of alkenes. So remember when we talked about that, if you're using ozone, right, and that zinc workup, if you have an alkene and it has an H in the vinylic position and you do the oxidative cleavage, one of the products when you cleave it is the aldehyde functionality. So we already know that way of making it. Okay, but now we want to talk about a new way. And it is the partial reduction of carboxylic acid derivatives. And we've kind of been introduced to this already, okay? And so when I say a partial reduction, what I'm saying is I want to be able to take a carboxylic acid derivative. And remember, our standard abbreviation for them now is to have my acyl fragment attached to a Y, because the Y is the leaving group. So any of those carboxylic acid derivatives, carboxylic acids, acid chlorides, esters, all of those are abbreviated this way. And what I'm looking at with a partial reduction is I'm saying, is there some way I can use a hydride reagent, like we talked about in the alcohol chapter, use this hydride reagent and partially reduce it, which effectively means adding one equivalent. because then it would stop at the aldehyde. Because remember, in practice, if you use the reducing agents we've already talked about, you'd have one equivalent of H do the substitution, and then you have the second hydride come in, and you'd end up with the alcohol. So what we're asking is, can you partially reduce that? Stop after one equivalent. Okay? Is that possible? And yes, it is. But it's going to mean that we have a different reducing agent than we talked about. Okay, because we talked about the fact that the standard reducing agent that we use with carboxylic acid derivatives, remember, was LAH. So if you had an ester and you treated it with LAH, it would reduce all the way to the alcohol. Okay, so we can't use LAH, there's got to be something different. So let's look at the case of an ester. Let's say we have this ester. There is a reducing agent that'll work, but it's different than sodium borohydride, and it's different than lithium aluminum hydride. It's something that's called Dibol. And it's abbreviated different ways in different books, but it's di, little I, ball. Okay? And you react it just like you would any other reducing agent, in that you react it with that reagent and then there's some kind of aqueous acid workup. But in this particular case, it stops after one equivalent, and you actually can obtain this as your product. No further reduction occurs. Okay? And therefore it is called a partial reduction. Now, how is it able to do that? How can you stop after that one addition? Okay? Well, it's going to have to do something with the reactivity of Dibol. So the first thing to do is look at the structure of Dibol. It's much different than lithium aluminum hydride, which doesn't have very much steric bias associated with it. Dibol is diisobutyl aluminum hydride. Diisobutyl aluminum hydride, Dibol. And it is a hydride reagent. But look at its structure. It has the aluminum and it has a hydride. But something like lithium aluminum hydride, remember, just had more hydrides on it and the counter ion that was the metal. But with with Dibol, you have this diisobutyl group that's attached. And these are what I call antlers, right? There's a lot of steric bias that's associated with this. So it reacts once just because it's not as reactive because of its steric bulk. But the other thing is it only has one hydride per molecule. And so it's easy to control the one equivalent. Both of those together are helpful, and therefore it can deliver this one hydride, okay, and its reactivity is less likely to react twice. Okay? All you really need to know is that Dibol is the reagent. So that example that I gave of it partially reducing an ester would be, that would be what you would put on the arrow of your flashcard. Okay, I'm looking at time. All right, so that is the way that you can prepare aldehydes. That's three ways. Two were review, and one is new. Okay, then now what about preparation of ketones? Okay, just like we saw with aldehydes, we already know some ways. So let's look at the review ones first. And I think what I'll do is I'll kind of list the review reactions for you, and then we'll wait till next lecture to talk about the new reactions. Okay, so the review, this will give you a chance to look back at it, is oxidation of secondary alcohols. Right? Because oxidation of secondary alcohols gave me ketones. Primaries gave me aldehydes or carboxylic acids. Secondary alcohols gave me ketones. The second is oxidative cleavage of alkenes. Same thing we saw with the aldehydes, but remember when you have an alkene, if it doesn't have a vinyl H on the alkene carbon, then when you do the cleavage, it's a ketone that forms. Okay, so again, that's review. And then the third is Friedel-Crafts acylation, right? We've seen this already. Okay, can you think of any others? I can. What about hydration of alkynes? Remember when we had an alkyne and we added water across the alkyne, it formed the enol, which then tautomerized to the keto form, so it formed the ketone. So all of these are review reactions, ways that you can prepare ketones. Okay? We will start next time with me telling you a new reaction. And Will, this is where I promised you earlier. Remember that whole thing about Grignard versus Gilman? This is where that's going to come into play, because just foreshadowing for next time, the new reaction is going to be basically a partial alkylation of a carbonyl compound. You remember how when we added Grignard to a carboxylic acid derivative, it would add twice and you get the alcohol? Well, kind of like we just saw with Dibol, is there a way that we can add an alkyl group to a carboxylic acid derivative and just do the substitution, stop after one equivalent is added? And the answer is yes, we can. Can't do it with Grignards, but we're going to see the way that we can do it, right? And so on that note, we will stop and begin next time with the new way of preparing a ketone.